I'm in outer space, far from anything else, and there are two masses. The first is 5 kilograms, and the other is 2 kilograms. Masses attract each other with the force of gravity. I'm going to take a third mass and place it somewhere in between the two so that the net gravitational force on M3 is 0. What if I put M3 in the middle? It is attracted to M1 and it's attracted to M2. But this mass doesn't pull as hard. The force on the right is weaker because M2 has less mass, so it produces a smaller gravity force. We know that because of Newton's law of universal gravitation. Any two masses are attracted according to this equation. So what do we have to do? When we take M3, it has to be closer to the small mass. And now, this force might be able to balance that force. I'll call the left the force of mass 1 pulling on mass 3. This is the force of mass 2 pulling on mass 3. Gravity attracts masses. In these problems, we're usually given the distance between the two masses. I'm going to make up a value and say that that's 10 meters. We also care about the distance from 1 to 3. I'll call that R13. And we care about the distance from mass 2 to mass 3. There are two crucial equations. First, these forces cancel, and the net force on M3 is 0. The second crucial equation, if I add these distances, what do I get? 10 meters. I'm going to use Newton's law of universal gravitation to plug in for the left and the right side. This left force is referring to the attraction between M1 and M3. So I care about those masses. I care about the distance between them, R13 squared. The right side, this F23 is referring to the gravitational attraction between M2 and M3. And I divide by the distance between those squared. The G's cancel out, the M3's cancel out, and look at this. I know M1, I know M2. This equation has two unknowns. This equation has the same two unknowns. I have a system of two equations. We can solve this using algebra. The easiest way to solve is to plug in the values. M1 is 5, M2 is 2. I'm going to isolate R23 so that I can plug in and remove R23 from this equation. That way I can solve for my unknown R13. To isolate R23, first I'm going to cross multiply. I have 5 R23 squared equals 2 R13 squared. I divide by 5. Did I get that mass right? M1 was 5, yep. And the final step is to square root both sides. I square root this, and I can distribute the square root to both factors. So I have R23 is radical 2/5 times R13. Now I take that formula and I plug in for R23. What was it? It was square root of 2/5 times R13. Well, this is like saying I have 1 times R13 plus radical 2/5 R13. Let's factor out R13. What do we have in parentheses? 1 plus radical 2/5. And that's being multiplied by R13. So to isolate, we divide both sides by this. And the answer is 10 meters over 1 plus radical 2/5. We can calculate that pretty easily. What if we have a problem where the two masses, 5 kilograms, and we'll make the other one 5 as well, they're still out in outer space, out in the middle of nowhere, so they're not sitting on the surface of the Earth. There isn't some mg force here where we multiply by 9.8, 9.81. That's not present because we're in outer space. We're not on Earth. And these two masses are originally separated by 4,000 meters. We let them go from rest, and they accelerate toward each other because they feel these attractive gravity forces. So they start at rest, but they begin to speed up. After some time, they're moving pretty fast toward each other, and they're much closer now. Now they're only 1,000 meters apart. How do we think about the speed here at the end? How do we think about the energy? Well, we know that there is conservation of energy. No forces act on these masses except for gravity. Gravity is a conservative force. There is no friction. There isn't a person coming along and giving this thing a push. There is no outside interference. So the total initial mechanical energy is conserved, and that means it's equal to the total final mechanical energy. Energy has different forms. It can include gravitational potential energy and kinetic. That's true at the beginning, and it's true at the end. But if the objects start from rest, there is no initial kinetic energy. So how do we solve this problem? Well, we know the equation for initial gravitational energy. It's negative g times the two masses, m times m, which is 5 times 5, or 5 squared, divided by their distance, not squared now, it's just the distance. Initially, they're 4,000 meters apart. On the right side, we put in the formula for u, which is given in the equation sheet. Negative g m1 m2 over r squared. The masses are both 5, so I have negative g times 5, or 5 squared. How far apart are they at the end? Only 1,000 meters apart. And finally, we have to add in the kinetic energy. This kinetic energy value represents the total kinetic energy of the whole system. After all, mechanical energy is the total energy for the whole system. So we could plug in the value of g, which is also in our equation sheet, 6.67 times 10 to the minus 11. And we could solve for how much kinetic energy is in the system. Where is that kinetic energy? It's in this mass, and it's in this mass. They're both moving. And because they have the same speed and the same acceleration and the same mass, because they have the same initial speed, they accelerate the same, they have the same mass, their final speed is going to be the same. So if we wanted, we could replace the K final, the final kinetic energy. Well, we've got two masses with the same final KE, or final kinetic energy, of 1/2 mv squared, where the mass is 5. So if I put in a 5 right here, 1/2 times 5 times v squared, we could solve for v if we wanted. We know the g value, and we know everything else in the equation. What if we have a problem where here is the Earth with some mass big M, here is an object with a mass little m, and it is spaced some distance r from the center of the Earth. And maybe r is something like 7, let's make it 1,000,000 meters. The mass of the Earth is roughly equal to 6 times 10 to the 24 kilograms for mass. The little m we don't need. What's the acceleration due to gravity? Right here, where this mass is located. Well, we know this thing feels a gravity force, and we have two equations for the gravity force. The first is the one that we're used to using from way back at the beginning of the year, mg, where g is the acceleration due to gravity at that point, and m is the mass located at that point. The other equation that we've learned, though, there is attraction because this little m is near this big mass of the Earth. So we plug in the two masses, which in this case are little m and big M. We divide by the square of the distance between their centers. And look at this, if we set the equations equal, the little m, the mass of this thing up way high, cancels out. So the acceleration due to gravity only depends on that constant g, this 6.67 times 10 to the minus 11, times the mass of the planet over r squared. So we could plug in these values and we could calculate. The square, don't forget the square, that's easy to do, of 1 times 10 to the 6 meters. What if we found this value, and I'm going to make up a number, I have no idea if this is correct. I'll say this is just 2 meters per second squared. Meters, seconds to the negative 2, meters per second squared. And I want to know now, if this thing is orbiting, this mass m, how long does it take to make one full revolution? Well, the first equation that we know is speed is distance over time. So let's see. In one revolution, the time that passes is called the period. The distance we travel is the circumference. How does that help me? Well, this thing out here, this mass, believe it or not, is in free fall. It's a weird idea, but anything that's orbiting is in free fall. And that's because free fall is defined as having just the force of gravity acting on you. The only thing that pulls down is gravity. I mean, there's no other forces around, there's no air resistance. There isn't tension because we're not connected to a string that goes all the way to the Earth. There's no wall, there's no surface, no normal force that this thing is resting on. So the only force is the force of gravity. That means the acceleration is the acceleration due to gravity. So the value we found, that 2 meters per second squared, is equal to the object's acceleration, but this is a centripetal acceleration because it's moving in a circle. So in place of AC, we could put v squared over r. That's one of the formulas from our book, from our equation sheet. We know the value of r, so we could find the speed. And once we find the value of speed, which is just going to be the square root of gr, right, this was g. Once we find the speed, we could plug it in right here and set it equal to 2 pi r over t. And from here, we can solve for t if we know g and if we know the r value. When an object is in orbit around some mass m, here's some little thing, little m, in orbit, there is another way to find the speed. We know that the gravity force is what provides the centripetal net force. And the gravity force is g times the product of the masses over the distance between them squared. But the centripetal net force, well, what's Newton's second law say? Net force is mass times acceleration. This is the centripetal acceleration. Again, m cancels, one of the r's cancel, and the speed is radical gm over r. So if you know the mass of the planet and the orbital radius, you can find the speed.